Welcome to Sleeping Researcher, where we gently explore the wonders of science through calm and soothing narration, guiding you into restful sleep. Today, we will journey deep beneath our feet and through the vast expanse of time, uncovering the remarkable story written in the very layers of the Earth itself. Each stratum of rock, every sediment holds secrets of our planet's geological past and the climates that have shaped life as we know it. Before we begin, if you find comfort and curiosity in this peaceful exploration, please consider liking this video and subscribing to Sleeping Researcher. Your support helps us continue to bring you calming science stories designed to relax your mind and ease you into sleep. Now, let us embark on a slow and gentle voyage through Earth's layers, where stone and soil become pages of an ancient, unfolding story. Imagine the Earth as a vast history book with chapters written in minerals and fossils, in shifts of temperature and changes in atmosphere. From fiery volcanic eruptions to tranquil ocean beds, from icy glaciations to lush ancient forests, the layers beneath us record these dramatic shifts. By studying these geological records, scientists can piece together the rhythms of Earth's climate through millions of years, revealing patterns of change and stability. As we move softly through this narration, allow your mind to drift with the slow passage of time, connecting with the silent stories held deep within the Earth. Together, we will explore how these layers not only tell us where we have been, but also guide us toward understanding our planet's future. Imagine holding in your hands a book so vast and ancient that its pages stretch back billions of years. This is the story held within the layers of our planet, Earth. Each stratum, from the deepest crust to the uppermost sediments, represents a chapter in the intricate history of our world. These layers act as natural archives, silently preserving the evidence of shifting climates, tectonic movements, and the gradual evolution of life itself. As we delve into the geological and climate history embedded in Earth's layers, we begin to understand how our planet has transformed over unimaginable spans of time, revealing secrets that help us appreciate the delicate balance sustaining life today. Beneath our feet, the Earth's crust is composed of sedimentary rocks, each layer forming over millennia as particles settle and compress. These layers capture snapshots of ancient environments, from scorching deserts to lush forests, locked in the minerals and fossils they contain. By studying these sediments, scientists can reconstruct past climates, identifying periods of warmth and ice, shifts in atmospheric composition, and even ancient ocean currents. The chemical signatures within these rocks serve as subtle clues, whispering stories about volcanic eruptions, mass extinctions, and the gradual drift of continents. Through this layered record, we trace the ever-changing face of our planet, understanding that Earth's surface is far from static, but constantly reshaped by dynamic forces. Deeper still, the Earth's mantle and core, though inaccessible, contribute to the story through their influence on surface geology. Movements within the mantle drive plate tectonics, causing continents to collide, mountains to rise, and ocean basins to form. These tectonic processes leave their mark in the rock record, preserved as folded strata, mineral veins, and fossil assemblages that mark the passage of time. Climate history is intertwined with these geological changes, as shifts in the arrangement of continents impact ocean circulation and atmospheric patterns, thus influencing global climates and ecosystems. The Earth's layers are therefore more than mere rock. They are a dynamic archive of interactions between the solid planet and its fluid atmosphere and oceans. Ice cores and sediment layers from polar regions and ocean floors further enrich this record, offering high-resolution glimpses into past climates. These natural time capsules capture trapped gases, pollen, and microscopic organisms, allowing scientists to reconstruct temperature fluctuations, greenhouse gas concentrations, and even patterns of rainfall across millennia. The interplay of geological and climatic data from these layers helps us comprehend not only Earth's past, but also provides a valuable context for understanding current changes in our environment. Thus, Earth's layered history is a profound testament to the planet's resilience and the intricate connections that have shaped its journey. In the earliest epochs of our planet, approximately 4.5 billion years ago, Earth was a molten sphere, an intense ocean of magma and vapor. This fiery infancy was marked by relentless heat and constant bombardment from cosmic debris. As the planet gradually cooled, a remarkable transformation began to unfold beneath the churning surface. Minerals started to crystallize and solidify, giving rise to the very first solid skin of our planet, the primordial crust. This fragile, thin layer was the foundation upon which all subsequent geological processes would take place. It was the birth of Earth's crust that set the stage for the preservation of an intricate and dynamic record of our planet's history. A record written in stone and layered deeply beneath our feet. Over immense spans of time, the early crust underwent continuous changes, driven by internal heat and external forces. The process of differentiation separated lighter materials from denser ones, allowing the formation of distinct layers within Earth. Volcanic activity brought new material from the mantle to the surface, while tectonic movements began to shape the crust structure. These shifting plates fractured, collided, and sometimes sank beneath one another, a process that sculpted the continents and ocean basins we recognize today. Each geological event left signatures within the layers, traces of volcanic eruptions, sediment deposits, and metamorphic transformations that serve as chapters in Earth's vast geological narrative. Through the study of these layers, scientists decode the timeline of crustal evolution and the planet's changing face. Embedded within the Earth's crust are clues that reveal not only the mechanics of its formation, but also the climatic conditions that prevailed through different eras. Sedimentary layers, formed from compacted particles of rock and organic matter, often contain fossils and chemical markers that reflect ancient environments. The interplay between geological formations and climatic shifts is recorded in these strata, showing how Earth's surface responded to changes in temperature, atmospheric composition, and sea levels. For instance, glacial deposits indicate periods of extensive ice coverage, while coal seams suggest dense, lush vegetation during warmer intervals. This intertwined record allows researchers to trace cycles of warming and cooling, revealing the planet's long-term climate variability, driven by both internal and external forces. The preservation of Earth's geological and climatic history within its layers is a delicate balance, maintained by the slow but persistent processes of erosion, sedimentation, and plate tectonics. Over millions of years, sediments accumulate in vast basins, burying older layers and protecting them from surface disturbances. Meanwhile, tectonic uplift can expose ancient rocks, providing windows into deep time. Modern techniques such as radiometric dating and isotope analysis allow scientists to assign precise ages to these layers, unlocking the timing of key events in Earth's history. By examining these records, we gain insight into the cycles of mountain building, ocean formation, and atmospheric evolution that have shaped the planet's habitability. Each layer offers a glimpse into a different chapter, collectively narrating Earth's complex and ever-changing story. Understanding the birth and evolution of Earth's crust is crucial for contextualizing the vast archive of geological and climatic data preserved within it. This foundational layer not only supports the continents and ocean floors, but also acts as a repository for the planet's memory. The continuous interaction between the crust and Earth's atmosphere, hydrosphere, and biosphere has guided the development of life and influenced climate over billions of years. As scientists delve deeper into these ancient records, they uncover the processes that have driven Earth's transformation from a molten ball to a vibrant world teeming with life. This exploration of Earth's earliest crust leads us naturally toward examining the dynamic forces of plate tectonics that continue to shape the planet today. Sedimentary rocks stand as one of nature's most eloquent storytellers, quietly recording Earth's history in their layered formations. These layers accumulate over vast stretches of time as particles of sand, silt, clay, and organic material settle in quiet waters or gentle winds. Each layer represents a moment or series of moments frozen in time, capturing the environmental conditions present during its deposition. Over millions of years, these sediments compress and solidify, creating strata that serve as pages in Earth's geological diary. From ancient riverbeds to ocean floors, from deserts to swamps, sedimentary layers preserve a rich tapestry of past landscapes, climates, and ecosystems. By studying these rocks, scientists gain valuable insights into the shifting patterns of sea levels, the rise and fall of continents, and the subtle changes in Earth's climate that have shaped the evolution of life itself. The formation of sedimentary layers is a delicate balance of geological processes where erosion, transportation and deposition work in harmony. As mountains erode under the influence of wind and water, tiny mineral grains are carried away, often traveling great distances before settling in basins or shallow seas. These depositional environments vary widely, from tranquil lakes and deep ocean trenches to river deltas and vast deserts. Each setting imparts distinct characteristics to the sediment, influencing grain size, composition, and layering patterns. Seasonal and climatic variations leave their mark as well, sometimes resulting in rhythmic layering or the inclusion of fossilized remains. Such fossils, embedded within sedimentary rocks, provide a biological context, offering clues about the species that thrived during particular epochs and the environmental stresses they endured. This intricate interplay of physical and biological factors transforms sedimentary layers into a multi-dimensional record of Earth's past. Beyond their physical composition, sedimentary layers serve as invaluable archives of ancient climate. Through the study of isotopic ratios, mineral content, and fossil assemblages, geologists reconstruct temperature fluctuations, atmospheric composition, and even patterns of precipitation from millions of years ago. For example, variations in oxygen isotopes within marine sediments reveal cycles of glacial advance and retreat, while the presence of certain clay minerals can indicate periods of aridity or humidity. These records are crucial for understanding long-term climate dynamics and help contextualize current climate trends within Earth's broader history. Each layer is a chapter in an ongoing narrative, chronicling how the planet's climate system has responded to volcanic activity, asteroid impacts, tectonic shifts, and the gradual influence of solar radiation. In essence, the sedimentary archive is a bridge connecting the deep past to the present, illuminating the forces that continue to shape our environment. As these sedimentary layers accumulate and lithify, they also undergo various transformations that further record Earth's dynamic history. Compaction and cementation solidify loose sediments into rock, while tectonic forces can tilt, fold, or fracture these layers, revealing their stories in cross-section. Such deformations provide insight into past geological stresses and the movement of Earth's plates. In some cases, sedimentary rocks are buried deeply enough to experience changes in mineralogy and texture without fully melting, a process known as metamorphism, which adds another layer of complexity to their history. Through careful fieldwork and laboratory analysis, geologists piece together these clues, reconstructing ancient environments with remarkable detail. By interpreting sedimentary layers alongside other geological evidence, scientists build comprehensive models of Earth's evolving surface and climate systems. This continuing journey of discovery naturally leads into the study of the tectonic processes that drive such profound changes. Among the most compelling records preserved within sedimentary rocks are fossils, remnants or traces of ancient lifeforms that have been gently encased by accumulating sediments over millions of years. These preserved organisms, whether they be shells, bones, leaves, or microscopic creatures, serve as direct evidence of the biodiversity that once flourished in particular environments. Fossils are not merely curiosities, they are fundamental to understanding the progression of life on Earth. When an organism dies and is rapidly buried by sediment, decay slows dramatically, allowing delicate structures to be preserved. Over time, mineral-rich waters percolate through the sediments, gradually replacing original organic material with minerals, a process known as permineralization. This transformation locks these biological artifacts into stone, providing a tangible link to past ecosystems. By studying the specific types of fossils found within particular sedimentary layers, scientists can reconstruct the habitats that existed during different geological periods, revealing shifts from ancient oceans to lush forests or vast deserts. Beyond capturing the forms of past organisms, fossils also offer invaluable clues about the environmental conditions that prevailed when they were alive. The nature of the sediment enclosing fossils, whether fine mudstone, coarse sandstone, or limestone, indicates whether the setting was a tranquil lakebed, a dynamic river delta, or a shallow marine shelf. Certain fossils, known as index fossils, are particularly useful because they existed during relatively short geological windows but were widespread geographically. Their presence helps geologists correlate layers across vast distances and date rocks with remarkable precision. Additionally, the orientation, abundance, and preservation of fossils can shed light on past climate factors such as temperature, salinity, and oxygen levels. For example, the discovery of coral fossils in what is now a temperate region suggests that the area once experienced much warmer, tropical conditions. Similarly, the study of fossilized pollen grains reveals changes in vegetation patterns tied to ancient climate fluctuations. These biological indicators, embedded within rock, weave together a narrative of Earth's climatic evolution through deep time. The fossil record also illustrates the profound impact of geological events on life's trajectory. Mass extinctions, marked by abrupt disappearances of numerous species within sedimentary sequences, reflect catastrophic environmental changes such as volcanic eruptions, asteroid impacts, or rapid climate shifts. By examining the layers above and below these extinction horizons, scientists can decipher the timing and potential causes of these dramatic turnovers. Moreover, the gradual appearance and diversification of new species in younger strata reveal evolutionary responses to changing habitats and conditions. Fossils thus serve as a biological archive, chronicling both the resilience and vulnerability of life amid Earth's relentless transformations. In some cases, exceptionally preserved fossils, known as Lagerstätten, offer exquisite detail of soft tissues and behavior, providing rare windows into ancient ecosystems. Each fossil assemblage contributes a vital piece to the puzzle, helping to illuminate the complex interplay between life and Earth's shifting environments. Advances in technology have deepened our ability to extract information from fossils embedded in rock. Techniques such as isotopic analysis of fossilized shells enable scientists to infer past ocean temperatures and chemical compositions, refining our understanding of paleoclimate. Imaging tools like CT scans reveal internal structures without damaging precious specimens, while molecular studies occasionally detect traces of ancient organic molecules, offering glimpses of genetic information long lost. Integrating these methods with stratigraphic data and sedimentology enriches the context in which fossils are interpreted. This multidisciplinary approach transforms rocks into dynamic records, where biological and environmental histories converge. Each fossil-bearing layer thus becomes a chapter in Earth's vast chronicle, inviting ongoing exploration and discovery. As we continue to delve into the stories locked within sedimentary layers and their fossil content, we come closer to understanding the intricate relationship between Earth's geological processes and its living inhabitants. These clues embedded in rock do more than reveal past life. They illuminate the shifting balance of climate, sea levels, and tectonics that have shaped our planet's surface. From microscopic life to towering dinosaurs, fossils chart a course through time that connects us to a world long vanished, yet eternally preserved beneath our feet. This unfolding narrative naturally guides us toward exploring the tectonic forces that have influenced sedimentation patterns and fossil distribution, leading into the next chapter of Earth's dynamic history. Within the vast archive of Earth's geological layers, volcanic ash deposits stand out as unique and invaluable records. When a volcano erupts, it spews fine particles of ash high into the atmosphere, which then settle over large areas, often covering landscapes far from the eruption site. These ash layers, known as tephra, are rapidly deposited and form distinct, thin bands within sedimentary sequences. Because volcanic ash contains minerals that can be precisely dated using radiometric techniques such as potassium-argon or argon-argon dating, these layers serve as reliable time markers. By identifying and correlating these ash horizons across different regions, geologists can synchronize the timing of geological and biological events with remarkable accuracy. This ability to pinpoint moments in Earth's history allows scientists to reconstruct the timing and sequence of environmental changes that have shaped the planet's climate and ecosystems over millions of years. Beyond their role as chronological anchors, volcanic ash layers also reveal episodes of profound environmental disturbance. Large volcanic eruptions can inject vast quantities of gases and aerosols into the atmosphere, temporarily altering global climate patterns. For example, sulfur dioxide released during explosive eruptions can form sulfate aerosols that reflect sunlight, leading to short-term cooling known as volcanic winter. These climate perturbations are often recorded in the sedimentary record, where ash layers coincide with shifts in temperature, precipitation, and ocean chemistry. In some cases, the environmental stresses triggered by intense volcanic activity are linked to mass extinction events. The layers of ash found in proximity to fossil assemblages show how sudden and dramatic these changes could be, affecting biodiversity on land and in the seas. By studying these volcanic signatures, scientists gain insight into the complex feedbacks between Earth's internal forces and surface environments. The chemical composition of volcanic ash also provides clues about the nature of eruptions and the tectonic settings in which they occurred. Different types of volcanoes produce distinct ash chemistries, which can be traced back to magma sources deep within the Earth's crust or mantle. By analyzing the mineralogy and geochemistry of ash layers, researchers can reconstruct past volcanic activity and its relationship to plate tectonics. For example, ash deposits associated with subduction zones often contain high levels of silica and volatile elements, reflecting the melting of oceanic plates beneath continental margins. Conversely, eruptions at mid-ocean ridges or hotspot volcanoes yield different ash characteristics. These geochemical fingerprints not only help identify eruption sources, but also enhance our understanding of how volcanic processes have evolved through geological time. This knowledge bridges the gap between surface climate records and the dynamic engine driving Earth's interior. In addition to serving as markers of time and agents of environmental change, volcanic ash layers influence sedimentation and fossil preservation. The rapid burial of ecosystems beneath ash can create exceptional conditions for fossilization, preserving delicate structures that would otherwise decay. This phenomenon offers snapshots of life immediately before and after volcanic events, capturing moments of ecological crisis and recovery. Moreover, the fine-grained ash can alter soil chemistry and water quality, impacting plant and animal communities over extended periods. By examining these interactions within the geological record, scientists uncover the interconnectedness of Earth's systems, how volcanic forces ripple through atmosphere, hydrosphere, and biosphere. Each ash layer becomes a chapter in a vast, unfolding story of transformation, resilience, and adaptation. As we continue to examine the intricate layers etched by volcanic activity, our journey leads naturally toward the broader tectonic movements that create these eruptions and shape the planet's surface. Understanding volcanic ash in the context of plate boundaries, mountain building episodes, and ocean basin formation brings us closer to grasping Earth's restless nature. The interplay between internal geodynamics and surface environments underpins much of the climate history preserved in rock. With this perspective, we step further into the dynamic narrative of Earth's past, poised to explore how shifting continents and evolving landscapes have left their marks in the geological record. As we delve deeper into the archives of Earth's climate, the frozen layers of ancient ice come into focus as invaluable time capsules. Ice cores, extracted from the vast ice sheets of Antarctica and Greenland, offer a unique glimpse into atmospheric conditions stretching back hundreds of thousands of years. Each successive layer of snow that is compacted into ice preserves tiny bubbles of ancient air, effectively trapping the composition of the atmosphere at the moment of snowfall. This natural preservation allows scientists to measure concentrations of greenhouse gases such as carbon dioxide and methane, providing direct evidence of how Earth's climate has fluctuated over glacial and interglacial cycles. The clarity and continuity of these records make ice cores indispensable for studying long-term climate trends, far beyond the reach of written history or even sedimentary archives. Through careful analysis, these frozen archives reveal the intimate relationship between atmospheric chemistry and global temperature, highlighting the delicate balance that sustains life on our planet. Beyond the capture of gases, ice cores also preserve isotopic signatures within the water molecules themselves, which serve as proxies for past temperatures. By examining ratios of heavy to light oxygen isotopes, researchers can reconstruct temperature variations with remarkable precision over tens of thousands of years. This method paints a detailed picture of how Earth's climate has responded to natural forces such as changes in solar radiation, volcanic eruptions, and shifts in Earth's orbit. These isotopic records often align with other geological evidence, such as sediment layers and fossil data, weaving a cohesive narrative of Earth's evolving climate system. Moreover, the stratigraphy of ice layers chronicles episodic events like massive volcanic ash falls, sudden methane spikes, and ancient dust storms, each leaving a distinct mark in the frozen record. Together, these data points help decode the complex feedback mechanisms that drive climate change, offering insight into the interactions between atmosphere, oceans, and biosphere. The value of ice cores extends beyond mere retrospective observation. They provide a framework to understand the pace and magnitude of current climatic shifts in context. By comparing past natural variability with recent atmospheric changes, scientists can discern the imprint of human activities on the environment. For instance, the unprecedented levels of carbon dioxide recorded in the uppermost layers signal a departure from natural cycles, underscoring the urgency of understanding these changes. The depth and breadth of the ice core record also illuminate the resilience and vulnerability of Earth's systems, showing periods of rapid warming and cooling, as well as relative stability. These insights emphasize the interconnectedness of geological processes and climate, reminding us that Earth's history is a continuous dialogue between its solid framework and the fluid envelope of air and water that surround it. As we continue to explore these frozen chronicles, we prepare to integrate this knowledge with other geological records that further enrich our understanding of Earth's dynamic past. Beneath the surface of Earth lies a complex and dynamic structure, where immense plates of the planet's crust slowly drift, collide, and reshape the landscape over millions of years. This grand process, known as plate tectonics, is fundamental to understanding how Earth's geological layers are formed, altered, and sometimes erased. As tectonic plates move, they exert powerful forces on the rock strata, bending them into folds, lifting them into towering mountain ranges, or fracturing them along fault lines. These movements do not occur in isolation, but interact continuously with the processes of sedimentation, erosion, and volcanic activity. all contributing to the intricate layering of Earth's geological record. The layers we study today, visible in cliffs, canyons, and beneath the ocean floor, represent a palimpsest of shifting boundaries and ancient environments, preserved yet often distorted by the relentless motion of the plates beneath our feet. The folding and uplifting of rock layers by tectonic forces reveal much about Earth's history, but they also present challenges to geologists trying to read the story embedded in the stones. When plates converge, the immense pressure can crumple sedimentary layers, twisting them into complex folds that obscure their original sequence. In some cases, older rocks are thrust over younger ones, reversing the natural order and requiring careful interpretation to unravel the true chronology. Uplifted mountain ranges, such as the Himalayas or the Rockies, expose deep layers that were once buried far beneath the surface, offering rare glimpses into conditions from eons past. However, this same uplift brings these rocks into contact with atmospheric and weathering processes that gradually wear them down, erasing parts of the geological record. The interplay between constructive tectonic forces and destructive surface erosion constantly rewrites the history inscribed in Earth's layers, reminding us that the record is both preserved and in flux. In addition to folding and uplift, tectonic activity can lead to the formation of faults, where layers of rock are broken and displaced. These fractures can offset or even obliterate sections of the geological record, creating discontinuities known as unconformities. Within fault zones, rocks may be crushed or melted, further complicating the story they tell. Subduction zones, where one plate slides beneath another, are particularly effective at erasing layers, as the descending material is recycled into the mantle, removing entire chapters from Earth's surface history. Yet, these zones also generate volcanic arcs and earthquakes, processes that forge new rock layers and reshape the surface anew. Thus, tectonics acts as both a sculptor and an editor of the geological narrative, continually modifying the surface and subsurface architecture. By studying these disruptions, scientists gain insights into the timing and nature of tectonic events, and how they have influenced global climate, ocean circulation, and biological evolution through time. The record preserved within Earth's layers is therefore a mosaic of continuity and interruption, a testament to the planet's restless interior and its interaction with the surface environment. Understanding how tectonic processes fold, uplift, and erase parts of this record allows us to appreciate the complexity of reconstructing Earth's past. It also highlights the need to integrate multiple lines of evidence, from sedimentary deposits to fossil assemblages and isotopic signatures, to build a coherent picture of ancient climates and landscapes. Each layer, each fold, each fault carries clues not only about the physical forces at work, but also about the environmental conditions that prevailed when they were formed. As we delve deeper into this geological tapestry, our perspective expands beyond static snapshots to a dynamic and evolving Earth, where the past is continually rewritten beneath our feet. While While the relative order of rock layers offers valuable insight into the sequence of geological events, it is the method of radiometric dating that allows scientists to assign precise absolute ages to these layers. This technique harnesses the natural process of radioactive decay, where unstable isotopes within minerals gradually transform into stable daughter isotopes at a predictable rate. By measuring the proportions of parent and daughter isotopes in a rock sample, geologists can calculate the time elapsed since the rock crystallized. This absolute timeline transforms our understanding of Earth's history from a simple sequence of events into a detailed chronology, revealing the timing of mountain building, volcanic activity, and sediment deposition with remarkable accuracy. The beauty of radiometric dating lies in its foundation on fundamental physical laws that have remained constant over billions of years. Elements such as uranium, potassium, and carbon decay at specific rates characterized by their half-lives, spanning timescales from thousands to billions of years. For ancient rocks, uranium-lead dating provides a window into the deep past, allowing scientists to date formations that are billions of years old. For more recent sediments, carbon-14 dating offers insights into events within the last 50,000 years. By selecting the appropriate isotopic system, researchers can unlock the age of rocks and fossils across a vast temporal spectrum. This precision complements the relative dating provided by stratigraphy and fossil correlation, creating a cohesive framework that integrates absolute and relative time. Radiometric dating also plays a crucial role in reconstructing Earth's climate history. By determining the ages of sedimentary layers and the fossils contained within them, scientists can correlate these findings with global climatic events such as ice ages, greenhouse intervals, and mass extinctions. This chronological context enables researchers to study how climate has changed over millions of years and how life on Earth responded to these changes. For example, dating volcanic ash layers interbedded with sedimentary rocks can pinpoint the timing of abrupt climate shifts or ecosystem turnovers. These precise timestamps help to unravel the complex interactions between the atmosphere, oceans, and biosphere, shedding light on the forces that have shaped Earth's climate through deep time. The integration of radiometric dating with other geological and paleontological evidence continues to refine our picture of Earth's dynamic past. As analytical techniques become more sophisticated, scientists can date ever smaller samples with increased accuracy, opening new windows into previously inaccessible chapters of Earth's story. This synergy between dating methods and geological observations enriches our understanding of processes such as plate tectonics, erosion, and sedimentation, and their influence on the planet's evolving climate. Each precisely dated rock layer thus becomes a page in the grand narrative of Earth's history, inviting us to explore the intricate interplay between the physical world and the passage of time. Deep within the geological record lies a profound testament to one of Earth's most transformative episodes. the Great Oxygenation Event, which occurred approximately 2.4 billion years ago. This moment in deep time marks the first significant rise of oxygen in the atmosphere, a change so profound that it altered the course of life and the chemistry of the planet itself. The evidence for this dramatic shift is preserved in ancient rock formations known as banded iron formations, or BIFs. These distinctive layers of alternating iron-rich minerals and silica-rich chert capture a snapshot of the delicate balance between oxygen production and the chemical environment of early oceans. The iron in seawater, once abundant and soluble under reducing conditions, began to precipitate as iron oxides when oxygen produced by photosynthetic microorganisms started to accumulate. The resulting iron deposits settled onto the seafloor, creating the striking bands that geologists study today. These rocks not only bear witness to the changing atmosphere, but also to the intricate interactions between life and the planet's environment. The formation of banded iron formations is closely linked to the activity of cyanobacteria, microscopic organisms capable of photosynthesis, which began producing oxygen as a byproduct. Before this biological innovation, Earth's atmosphere and oceans were largely anoxic, meaning they contained little to no free oxygen. The oxygen produced reacted readily with dissolved iron in the oceans, preventing its accumulation in the atmosphere. Only after iron was largely sequestered into these sedimentary layers could oxygen begin to build up in the atmosphere. This gradual oxygenation fundamentally reshaped the planet's surface chemistry and paved the way for the evolution of more complex, oxygen-dependent life forms. The layers of BIFs represent a geological ledger, chronicling the ebb and flow of oxygen and iron through time. By studying their composition, thickness, and distribution, scientists gain insights into the pace and extent of atmospheric change, as well as the environmental conditions that governed early microbial ecosystems. Beyond their mineralogical significance, banded iron formations offer a window into Earth's climatic conditions during the Paleoproterozoic era. The Great Oxygenation Event coincided with dramatic shifts in global climate, including episodes of widespread glaciation, sometimes referred to as snowball Earth events. The rise in atmospheric oxygen may have contributed to the reduction of greenhouse gases like methane, leading to cooler global temperatures. As oxygen levels fluctuated, the composition of the atmosphere changed, influencing patterns of evaporation, precipitation, and ocean circulation. These changes are subtly encoded in the sedimentary record, preserved within the strata that harbor banded iron formations. By correlating geochemical data with radiometric dating, researchers reconstruct a narrative of environmental upheaval, biological innovation, and climatic feedbacks that shaped the trajectory of Earth's evolution. The study of banded iron formations and their connection to the Great Oxygenation Event underscores the profound interplay between biology and geology. It reveals how microscopic organisms could drive planetary-scale transformations, altering atmospheric composition and surface chemistry over millions of years. These ancient rocks continue to inspire scientific inquiry, as each layer presents clues about the timing, mechanisms, and consequences of early oxygenation. Modern analytical techniques, including isotope geochemistry and high-precision dating, enable researchers to probe these formations with increasing detail, unraveling the story of Earth's early environment. As this chapter of our planet's history unfolds from the rock record, it invites us to contemplate the delicate balance of factors that sustain life and shape planetary habitability. As we delve deeper into the records preserved within Earth's crust, we prepare to explore the subsequent chapters in the planet's climatic and biological evolution. The Great Oxygenation Event set in motion a cascade of changes that would eventually lead to the rise of complex life. In the layers that follow, scientists observe further atmospheric transformations, shifts in ocean chemistry, and evidence of evolving ecosystems. These transitions are etched into sedimentary sequences that chronicle the ongoing dialogue between the biosphere and the geosphere. By continuing this journey through time, we gain perspective on the enduring processes that have sculpted Earth's environment and fostered its remarkable diversity. Within the vast archives of Earth's geological layers, moments of sudden and profound change are often recorded with striking clarity. These are the mass extinctions, intervals in deep time when many species vanished in relatively brief spans. Such cataclysmic events leave unmistakable signatures in the rock record, where changes in sediment composition and fossil assemblages reveal the story of life disrupted. For example, layers rich in iridium or abrupt shifts in carbon isotopes suggest dramatic environmental upheavals, often linked to volcanic activity, asteroid impacts, or rapid climate shifts. These chemical fingerprints, paired with the sudden disappearance or emergence of particular fossils, offer scientists a window into the ancient crises that reshaped biodiversity on a global scale. Among the most studied of these extinction events is the Permian-Triassic boundary, approximately 252 million years ago, often referred to as the Great Dying. This event stands as the most severe extinction recorded in Earth's history, eradicating an estimated 90% of marine species and a significant portion of terrestrial life. The geological record at this boundary captures a dramatic shift in rock chemistry, including elevated levels of carbon dioxide and evidence of widespread ocean anoxia, conditions that would have been inhospitable to many forms of life. Fossils abruptly vanish or become sparse, replaced by new assemblages that signal a profound biological reset. By examining these layers, researchers piece together the complex interplay of factors: massive volcanic eruptions, climate warming, and disrupted ecosystems that converge to drive this catastrophic die-off. Beyond the Permian event, Earth's strata reveal a succession of other extinction intervals, each marked by unique geological and biological signatures. For instance, the end Cretaceous extinction, famously associated with the demise of the non-avian dinosaurs, is recorded in a thin but distinct layer enriched with extraterrestrial elements, signaling the impact of a large asteroid. This boundary layer contrasts sharply with the layers above and below, where fossil content and sediment structures differ markedly. Such abrupt alterations in the fossil record and rock chemistry underscore the suddenness and severity of these extinction episodes. These geological chapters not only tell of loss, but also of resilience, as ecosystems eventually recovered and new life forms emerged, adapting to altered environments. The study of mass extinction markers within Earth's layers extends beyond identifying past catastrophes. It also provides insight into the mechanisms of environmental change and biological recovery. Chemical proxies such as shifts in oxygen and carbon isotopes inform us about past atmospheric and oceanic conditions, revealing patterns of warming, cooling, or acidification. These data, combined with fossil evidence, help reconstruct the pace and scale of ecological collapse and renewal. Through this lens, the rock record becomes a dynamic narrative, illustrating the delicate balance between life and the planet's physical systems. Such understanding enriches our appreciation of Earth's deep time history, while offering lessons about the resilience and vulnerability of life in the face of rapid change. As we continue to trace the intricate lines etched in stone, these mass extinction horizons guide us toward a deeper comprehension of Earth's evolutionary journey. Each disrupted layer invites us to reflect on the complex interactions among geological forces, climate fluctuations, and living organisms. In the layers that follow, we begin to observe the rise of new ecosystems and climatic regimes, shaped in part by the legacies of these ancient upheavals. With gentle patience, the sedimentary record unfolds further, revealing the ongoing story of transformation and adaptation that continues to this day. As we immerse ourselves deeper into Earth's layered history, we encounter the telltale signatures of ancient ice ages, preserved in the very rocks beneath our feet. These periods of profound global cooling left behind unique geological markers, such as glacial deposits known as tillites. Tillites are sedimentary rocks formed from the compacted sediments directly deposited by glaciers, comprising a mixture of clay, sand, gravel, and larger stones. Their presence in the geological record speaks volumes about the timing and extent of past glaciations, marking intervals when vast ice sheets advanced across continents. These deposits are often found interspersed with other sedimentary layers, acting as frozen chapters in the story of Earth's fluctuating climate. Alongside Tylides, another subtle yet powerful clue to ancient glaciations lies in the form of striations etched onto bedrock surfaces. These long, narrow grooves and scratches are carved by rocks and debris embedded in moving glaciers as they slowly grind across the Earth's crust. Striations not only indicate the presence of past ice masses, but also reveal the direction of glacier movement, helping scientists reconstruct the dynamics of ice flow during different ice ages. By examining these scratch marks and the associated Tylides, geologists gain insight into the extent of glacial coverage and the climatic conditions that prevailed during those cold epochs. Such evidence stretches back hundreds of millions of years, reminding us that Earth's climate system has undergone dramatic swings, shaped by complex planetary processes. The study of glacial deposits and striations extends beyond mere identification. It opens a window into understanding the broader climate mechanisms that orchestrated these ice ages. Factors such as variations in Earth's orbit, atmospheric greenhouse gas concentrations, and continental configurations all played crucial roles in triggering and sustaining glacial periods. By correlating tillite occurrences and striation patterns with other geological and geochemical data, scientists piece together a timeline of climatic shifts and their global impacts. These investigations reveal not only the harshness of the ice ages, but also the resilience of life forms adapting to changing conditions. The frozen footprints preserved in stone thus serve as a testament to Earth's dynamic climate history, a record inscribed patiently over eons. As we continue our exploration of glacial evidence, it becomes apparent that these ancient ice ages were not isolated events, but part of a recurring rhythm in Earth's environmental narrative. The layers of tillites and the intricate patterns of striations remind us that glaciers have sculpted the planet's surface over vast timescales, influencing ocean circulation, sea levels, and even the distribution of ecosystems. Each glaciation left an enduring imprint, setting the stage for subsequent geological and biological transformations. With this understanding, we prepare to delve into the next chapters of Earth's climate saga, where the interplay between ice, sea, and life continues to unfold. Beneath the vast expanse of the world's oceans lies a quiet archive of Earth's climatic past, patiently recording the subtle shifts and grand transformations of our planet's environment. Ocean sediments, formed from the slow accumulation of microscopic organisms, mineral particles, and chemical deposits, settle gently onto the seafloor, creating layered histories that span millions of years. These sediment layers are not merely inert deposits. They are dynamic chronicles that reveal how the Earth's climate has waxed and waned through time. By extracting deep-sea sediment cores, scientists can peer back through these layers, uncovering evidence of temperature changes, ice volume fluctuations, and even shifts in ocean circulation patterns. Each layer is like a page in a book, encoding information through the types of preserved microfossils, isotopic compositions, and sediment characteristics. Together, they form a timeline that helps us understand how natural forces have shaped the climate, responding to both internal processes and external celestial influences. Among the most compelling revelations from ocean sediment studies is the recognition of cyclical climate patterns, particularly the repeating ice ages that have marked the recent geological epochs. These glacial interglacial cycles are closely linked to variations in Earth's orbit and axial tilt, known collectively as Milankovitch cycles. These slow, predictable changes in the way Earth moves around the Sun alter the distribution and intensity of solar radiation reaching the surface, setting in motion profound shifts in climate over tens of thousands of years. Deep-sea sediments capture these rhythms with remarkable clarity, as changes in isotopes of oxygen within foraminiferous shells reflect global ice volume and ocean temperatures. This isotopic dance within the sediments reveals a pattern of cooling and warming phases, echoing the cosmic choreography that drives Earth's long-term climate variations. Through this lens, the ocean floor becomes a mirror, reflecting the celestial mechanisms that govern the planet's environmental pulse. The study of these sediment cores also illuminates the intricate feedback loops between the ocean's atmosphere and cryosphere, highlighting how interconnected Earth's systems truly are. As ice sheets advance and retreat in response to orbital forcing, their influence extends beyond the poles, triggering changes in sea level, ocean circulation, and atmospheric composition. The chemical signatures preserved within ocean sediments offer clues about past carbon dioxide levels, revealing how greenhouse gases have fluctuated alongside temperature and ice volume. These interconnected shifts underscore the delicate balance that sustains Earth's climate, where even subtle variations can ripple through multiple components of the global system. By examining these sediment records, scientists gain a deeper appreciation for the complexity and sensitivity of our planet's climate engine, emphasizing the importance of understanding past cycles to anticipate future changes. The ocean sediments, therefore, stand as a testament to Earth's evolving climate story, chronicled with patient precision beneath the waves. As we immerse ourselves further into this underwater archive, it becomes clear that the sediments do more than just record the past. They also guide us in interpreting the subtle nuances of climate dynamics that have shaped the biosphere. Variations in sediment grain size, organic content, and mineral composition reveal shifts in ocean productivity and circulation patterns, which in turn influence global climate feedbacks. The rhythm of these changes, laid down over millennia, helps reconstruct the timing and intensity of glacial cycles and interglacial warm periods. This detailed record not only enriches our understanding of natural climate variability, but also frames the context within which modern climate change unfolds. By recognizing these ancient patterns preserved in the ocean's depths, we gain valuable insights into the forces that regulate Earth's climate system on geological timescales. From this vantage point, the story of ice, sea, and life continues to reveal itself with quiet persistence beneath the ocean's surface. Coral reefs stand as remarkable sentinels of Earth's environmental past, their intricate structures silently chronicling the subtle dance between ocean and atmosphere. These living architectures grow in delicate layers, each one a testament to the conditions prevailing at the time of its formation. By examining the thickness and composition of these successive layers, scientists can infer fluctuations in sea level and ocean temperature across centuries and even millennia. The calcium carbonate skeletons of corals incorporate isotopes and trace elements that vary with water temperature and chemistry, effectively encoding a natural diary of climatic shifts. As sea levels rise or fall, coral growth responds accordingly, either expanding upward towards sunlight or retreating, thereby preserving a vertical record of historical ocean heights. This intimate relationship between coral growth and environmental parameters offers invaluable clues to understanding past climate variability and the interplay of oceanographic forces. Within these coral layers, the subtle variations in isotopic ratios, such as oxygen isotopes, serve as precise thermometers of ancient seas. Cooler periods tend to enrich coral skeletons with heavier isotopes, while warmer intervals leave a lighter signature. Through meticulous analysis, researchers reconstruct past ocean temperatures and correlate these findings with known climatic events, including glacial advances and retreats. Moreover, coral reefs are sensitive to changes in salinity and nutrient levels, factors influenced by rainfall patterns and ocean circulation. Thus, the reef records extend beyond temperature alone, revealing a more holistic picture of marine conditions over time. When combined with other geological archives, coral data help weave a detailed tapestry of Earth's shifting climate, illustrating the ebb and flow of ice ages and interglacial warmth. The adaptability of coral reefs to changing sea levels also provides a direct measure of the pace and magnitude of these shifts. During periods when glaciers melted and sea levels rose rapidly, corals often responded by growing vertically, striving to maintain their position within the sunlit surface waters necessary for photosynthesis. Conversely, falling sea levels could expose reefs, halting growth and sometimes causing widespread reef mortality. These growth patterns, preserved in fossilized reef terraces, offer a window into the timing and extent of ancient sea level changes. By mapping these terraces globally, scientists gain insights into the interconnected forces driving ocean volume changes, including ice sheet dynamics and thermal expansion of seawater. The coral reef record thus becomes a powerful tool to understand the natural variability of sea levels and their impact on coastal ecosystems through geological time. Beyond their geological significance, coral reefs also illuminate the complex feedbacks between climate and the biosphere. As climate warms, changes in ocean temperature and chemistry can stress corals, altering their growth rates and skeletal composition, which in turn affects the information recorded in their layers. By studying both living and fossil corals, scientists can discern how past ecosystems responded to climatic perturbations, offering a glimpse into the resilience and vulnerabilities of marine life. This perspective is especially poignant today as modern reefs face unprecedented changes. The ancient coral layers remind us that the ocean's story is one of continuous adaptation and change, recorded patiently in stone beneath the waves. Each layer contributes to a broader understanding of Earth's climate system, setting the stage for further exploration into the forces shaping our planet's future. As we reflect on the delicate archives preserved within coral reefs, it becomes apparent that these formations serve not only as biological structures, but also as geological timekeepers. Their growth patterns, isotopic signatures, and spatial distribution collectively narrate a tale of shifting seas and evolving climates. This story is intricately linked to the broader processes of Earth's geological history, where the interplay of ice, ocean, and life continues to sculpt the planet's surface. From this vantage, our journey leads us deeper into the layers of Earth's history, where other natural records await to reveal the enduring dialogue between the planet's interior and its atmospheric envelope. Within the layers of Earth's crust lies a subtle yet profound record of ancient environmental change, inscribed through the ratios of carbon isotopes preserved in sedimentary rocks. Carbon, a fundamental element of life, exists primarily in two stable isotopic forms, carbon-12 and carbon-13. These isotopes do not just passively accumulate, rather, their relative abundance within organic and inorganic materials shifts in response to the balance of carbon reservoirs across the planet. When living organisms preferentially absorb the lighter carbon-12 isotope during photosynthesis, the resulting organic matter exhibits a distinct isotopic signature. Over geological timescales, variations in these signatures, locked within rock strata, become invaluable clues that reveal fluctuations in the global carbon cycle, reflecting changes in atmospheric composition, ocean chemistry, and biological productivity. The subtle shifts in carbon isotope ratios thus serve as an ancient ledger, chronicling the dynamic interplay between Earth's biosphere and its physical environment. As sediment accumulates layer by layer, the carbon isotopic record becomes a timeline, capturing moments when the dance of carbon through Earth's systems altered the climate and environment. Dramatic excursions in carbon isotope ratios have been linked to pivotal events such as mass extinctions, ocean anoxic events, and shifts in global temperature. For instance, a relative depletion of carbon-13 in marine carbonates often indicates an influx of carbon-12-rich organic carbon into the ocean atmosphere system, suggesting episodes of increased organic carbon burial or massive releases of methane from oceanic reservoirs. These perturbations in the carbon cycle not only reflect biological and geological processes, but also drive changes in greenhouse gas concentrations, influencing Earth's climate over millions of years. Through careful analysis of isotopic compositions in rock layers, scientists can reconstruct these ancient carbon fluxes, gaining insight into how Earth's systems responded to natural forcings and feedbacks long before human influence. The intimate connection between carbon isotopes and climate history is further revealed by examining the isotopic composition of fossilized organic matter and carbonate minerals. Variations in these records provide evidence for shifts in primary productivity, ocean circulation, and the sequestration of carbon in sediments. During periods of widespread organic carbon burial, for example, the atmosphere may have experienced a drawdown of carbon dioxide, potentially triggering global cooling and glaciation events. Conversely, releases of carbon-rich gases can lead to warming phases, altering precipitation patterns and the distribution of ecosystems. By integrating isotopic data with other geological proxies, we begin to perceive a complex and evolving portrait of Earth's carbon cycle, one that has oscillated between stability and disruption, shaping the conditions for life's persistence and transformation over eons. These revelations underscore the profound role carbon isotopes play as windows into Earth's ancient climate mechanisms. Beyond individual events, carbon isotope records also illuminate longer-term trends, charting the gradual evolution of Earth's atmosphere and biosphere. Over hundreds of millions of years, shifts in isotopic signatures correspond with the rise and fall of biological groups, tectonic reorganizations, and changes in volcanic activity. Each of these factors influences the distribution and cycling of carbon in subtle yet measurable ways. For example, the proliferation of land plants during the Devonian period introduced new pathways for carbon burial, altering isotopic ratios preserved in sedimentary basins. Similarly, large igneous provinces and associated volcanic outgassing can inject isotopically distinctive carbon into the atmosphere, leaving telltale markers in the geological record. These intricate connections between Earth's internal processes and surface environments are etched into carbon isotope profiles, inviting us to explore the deep time narrative of carbon's journey through rock, air, and life. Through this lens, the story of Earth's climate history unfolds as a continuous dialogue between carbon reservoirs and the forces that shape them. As our understanding of carbon isotopes deepens, so too does our appreciation for the delicate balance that sustains Earth's climate system. The geological archive offers a profound lesson that the cycling of carbon through the atmosphere, oceans, and lithosphere is both a driver and a recorder of environmental change. By tracing these isotopic fingerprints, scientists unlock the rhythms of ancient carbon cycles, revealing how natural processes have regulated climate and life across vast stretches of time. This knowledge guides us toward a more nuanced perspective on present-day carbon dynamics and their potential future trajectories. With this insight, we turn our attention next to the broader interplay of Earth's geochemical cycles, where other isotopes and elements further illuminate the planet's evolving story. As we examine the stratigraphic record with ever greater precision, the most recent layers reveal a new chapter in Earth's geological narrative, one distinctly shaped by human hands. These uppermost sediments carry subtle yet unmistakable imprints of industrialization, urbanization, and global change. From the mid-20th century onward, the acceleration of fossil fuel combustion has altered the composition of atmospheric gases, leaving behind chemical signatures such as elevated carbon dioxide and methane concentrations. These changes are not confined to the atmosphere alone. They permeate soils, lake beds, and ocean sediments, where layers rich in heavy metals, synthetic compounds, and altered isotopic ratios accumulate. Such markers serve as a geological ledger, chronicling humanity's profound influence on Earth's surface and biogeochemical cycles. Within this recent sedimentary archive, the entwined story of technological progress and environmental consequence unfolds, inviting us to consider how future layers might reflect the choices we make today. One of the most compelling features of these contemporary geological layers is the presence of novel materials. Plastics, radionuclides from nuclear testing, and fly ash particles that have no natural precedent in Earth's history. These anthropogenic deposits are often dispersed globally, embedded in soils and sediments far beyond their points of origin. Their widespread distribution and persistence underscore the scale and reach of human activity, marking this era as unique in the geological timeline. Moreover, shifts in sedimentation rates and composition often correspond with land use changes, deforestation, and agricultural practices, which alter erosion patterns and nutrient cycles. These physical and chemical alterations are recorded in the strata, illustrating the complex interplay between human society and Earth's surface processes. By studying these layers, scientists are able to piece together a detailed and nuanced record of how human-induced changes are inscribed in the planet's geological fabric. In addition to chemical and physical indicators, biological remnants preserved in recent sediments provide further insight into the Anthropocene. Pollen grains, microfossils, and even DNA fragments reflect shifts in biodiversity and ecosystem responses to human pressures. For instance, altered species compositions in sediment cores reveal patterns of habitat loss, invasive species introduction, and climate-driven migration. These biological signals complement the geochemical markers, allowing researchers to reconstruct a comprehensive picture of environmental transformation over the last century. Such integrative studies highlight the interconnectedness of geological processes and living systems, demonstrating how human activities ripple through Earth's complex web of life and matter. This convergence of evidence from multiple scientific disciplines enriches our understanding of the Anthropocene as a distinct geological epoch. The recognition of this anthropogenic signature within Earth's layers has profound implications for both science and society. It challenges us to rethink the concept of geological time, acknowledging that human influence has become a dominant force, shaping the planet's future trajectory. By identifying the onset and extent of these recent changes within the stratigraphic record, geologists contribute to defining the Anthropocene's boundaries and characteristics. This emerging field of study not only documents human impact, but also provides a temporal framework for assessing environmental stewardship and sustainability. As we continue to explore these recent layers, the narrative of Earth's evolving story becomes ever more intertwined with our own, underscoring the responsibility inherent in our role as planetary stewards. Looking ahead, this awareness invites deeper exploration into the interplay between human activity and Earth's geological and climatic systems. Deep beneath our feet, the Earth preserves a meticulous archive of its past, within layers of rock, sediment, ice, and organic material. These geological layers act as pages in a vast, natural history book, telling stories of ancient climates, shifting continents, and evolving ecosystems. Each stratum records environmental conditions at the time of its formation, embedding clues about temperature, atmospheric composition, and ocean chemistry. Scientists carefully study these layers, using techniques such as radiometric dating, isotope analysis, and fossil examination to reconstruct Earth's climate history across millions of years. This geological record reveals cycles of ice ages and warm periods, volcanic eruptions, and mass extinctions, offering context for the planet's dynamic climate system. Understanding these patterns allows researchers to see how natural forces have influenced climate and how life on Earth has adapted to changing conditions over geological time. Beyond the rocks themselves, ice cores drilled from glaciers and polar ice sheets provide another vital archive of past climate. Layers of snow compacted over millennia trap tiny bubbles of ancient air, preserving samples of greenhouse gases like carbon dioxide and methane. By analyzing these trapped gases, scientists gain direct insight into the relationship between atmospheric composition and temperature fluctuations through epochs. In addition, sediment cores from ocean floors capture microscopic organisms whose remains respond sensitively to water temperature and chemistry, acting as proxies for past oceanic and climatic conditions. Together, these multi-layered records from land, ice, and sea build a comprehensive picture of Earth's climate system, revealing both gradual trends and abrupt events. This integrated approach helps us to understand the natural variability of climate and the factors that have driven its changes long before human influence. The rich data drawn from these geological and paleoclimatic archives feed directly into sophisticated climate models used to predict future scenarios. By providing a long-term baseline, this information calibrates models that simulate the interactions of the atmosphere, oceans, land surface, and ice. The geological record constrains estimates of climate sensitivity, the degree to which Earth's temperature responds to changes in greenhouse gas levels, and helps validate projections of warming trends and extreme weather events. Scientists also use this data to test hypotheses about feedback mechanisms, such as the release of carbon from thawing permafrost or changes in ocean circulation patterns, which could amplify or mitigate climate change. This rigorous scientific foundation strengthens our ability to anticipate future climate trajectories and informs policy decisions aimed at minimizing human impact. Moreover, the interplay between geological studies and climate modeling underscores the importance of understanding Earth as a complex, interconnected system. Geological records remind us that climate change is not a new phenomenon, but part of an ongoing natural process influenced by volcanic activity, solar cycles, and tectonic shifts. Yet the unprecedented rate of current change captured in the most recent layers reveals the distinct mark of human activity. By integrating past and present data, researchers can explore how feedbacks and thresholds might operate under future conditions, identifying potential tipping points that could lead to irreversible changes. This holistic perspective invites a deeper appreciation for the resilience and fragility of our planet's systems. Such insights guide the development of adaptive strategies and reinforce the urgency of sustainable stewardship. As we continue to delve into the rich archives held within Earth's layers, the evolving dialogue between geology and climate science opens new pathways for discovery. Advanced technologies, from satellite observations to machine learning algorithms, enhance our ability to interpret complex datasets and improve model accuracy. These advances foster an ever closer connection between past climate reconstructions and future projections, illuminating the consequences of our choices on a planet that has witnessed countless transformations. In this shared endeavor, the ancient Earth informs the unfolding story of our climate's future, urging thoughtful reflection and mindful action. The journey from deep time to tomorrow's horizon is guided by the layered wisdom beneath us, inviting continued exploration and understanding. The Earth's geological layers serve as an extraordinary archive, chronicling billions of years of planetary history. Yet, deciphering this record is far from straightforward. Rocks and sediments often bear the marks of multiple events that have overlapped, disturbed, or even erased parts of the story. Tectonic shifts, volcanic eruptions, erosion, and other natural forces can alter or obscure the original deposits, creating a complex puzzle for scientists to unravel. Each layer may contain clues to climate shifts, biological evolution, or catastrophic events, but these signals are interwoven with noise and subsequent alterations. Understanding the interplay of these factors is essential to reconstructing accurate timelines and climate models. This challenge demands patience and meticulous analysis, as researchers must carefully separate primary information from secondary changes to avoid misinterpretation. One of the most intricate difficulties arises from the overlapping nature of geological events. For instance, a sediment layer might have been laid down during a warm period, only to be later disturbed by glaciation or tectonic uplift. Such overprinting can complicate efforts to assign precise ages or environmental conditions to the strata. Additionally, chemical and physical weathering processes can alter the original composition of rocks, further masking the authentic signals of past climates. Scientists employ a variety of methods to address these complexities, such as radiometric dating techniques, isotopic analyses, and sedimentology studies. These approaches enable them to tease apart simultaneous or sequential occurrences, yet the inherent uncertainties remain a persistent aspect of geological interpretation. A keen awareness of these limitations is crucial in building robust, reliable narratives of Earth's ancient environments. Beyond physical disturbances, biological activity also leaves its imprint, sometimes complicating the geological record. Fossilized remains of plants and animals provide invaluable insights into past ecosystems and climates. But bioturbation, the mixing of sediments by living organisms, can redistribute materials within layers. This process blurs the boundaries between distinct geological periods and can mislead interpretations if not carefully accounted for. Moreover, abrupt events such as asteroid impacts or massive volcanic eruptions introduce sudden, dramatic changes that may be recorded unevenly across different regions. The challenge lies in correlating these localized signatures with broader global patterns, requiring a comprehensive and interdisciplinary approach. By integrating paleontology, geochemistry, and geophysics, scientists strive to reconstruct a coherent picture within this intricate mosaic. Despite these formidable challenges, the pursuit of understanding Earth's layered history continues to inspire scientific ingenuity. Modern technologies, including high-resolution imaging, advanced geochemical fingerprinting, and computational modeling, have greatly enhanced the ability to interpret complex records. These tools allow researchers to detect subtle variations within rock formations, identify previously hidden structures, and simulate past climate scenarios with increasing precision. Still, acknowledging the inherent imperfections and ambiguities in the geological archive fosters a humble respect for the planet's dynamic nature. Each discovery is a step closer to unraveling the profound narrative of Earth's ever-changing climate and geological evolution. In embracing these challenges, the scientific community deepens its connection to the ancient Earth beneath our feet. As we continue this exploration, it becomes clear that the Earth's layers are more than mere records. They are a complex dialogue between past processes and present understanding. Interpreting these intricate archives requires patience, collaboration, and constant refinement of methods. The overlapping events and disturbances etched into the rock tell stories of resilience and transformation, reminding us of the delicate balance that sustains life and climate. This awareness enriches our appreciation for the efforts behind every reconstructed timeline and climate model. With this perspective, we move forward, guided by the layered wisdom that connects deep time to the evolving future. In recent years, the field of paleoclimatology has witnessed remarkable progress, largely due to advances in technology that allow scientists to peer into Earth's past with unprecedented clarity. Sediment cores, extracted from ocean floors, lake beds and glaciers, serve as natural archives, preserving layers of material deposited over millennia. These layers hold vital clues about past climates, variations in temperature, atmospheric composition, and even biological activity. Modern analytical tools such as high-precision mass spectrometers and imaging techniques enable researchers to examine these sediments at ever finer scales, sometimes resolving changes that occurred over mere decades or even years. This level of detail transforms our understanding of climate dynamics, revealing subtle shifts and rapid events that were previously masked by broader averages. Such insights are crucial for discerning natural climate variability from human-induced changes. The ability to reconstruct these high-resolution climate records represents a significant leap forward, bridging gaps in our knowledge and providing a more nuanced narrative of Earth's environmental history. The integration of innovative methods has not only enhanced temporal resolution, but also expanded the types of environmental indicators accessible from sediment cores. Geochemical proxies, including isotopic ratios and trace element concentrations, allow scientists to infer past ocean temperatures, salinity, and even nutrient cycles. Likewise, biological markers such as pollen grains, microfossils, and ancient DNA offer windows into ecosystem responses to climatic shifts. The synergy of these diverse data sources enriches the context surrounding each layer, revealing complex interactions among the atmosphere, hydrosphere, and biosphere through time. With improved dating techniques such as radiocarbon calibration and tephrochronology, the chronological framework supporting these reconstructions becomes increasingly robust. These advancements collectively refine the timeline of key events, from glacial interglacial transitions to abrupt climate anomalies, deepening our grasp of the forces shaping Earth's climate system. Through this intricate mosaic of evidence, sediment cores emerge not only as physical records, but as dynamic storytellers, chronicling the evolving narrative of our planet. The pursuit of high-resolution climate records also fosters interdisciplinary collaboration, bringing together geologists, chemists, biologists, and climate modelers to interpret the data within a holistic framework. As each discipline contributes specialized knowledge and techniques, the resulting reconstructions become more comprehensive and reliable. For example, climate models informed by finely detailed sedimentary records can simulate past atmospheric circulation and ocean currents with greater accuracy, enhancing predictions for future scenarios. Furthermore, these records help identify thresholds and feedback mechanisms such as ice sheet dynamics and carbon cycle interactions that govern climate stability and change. By examining periods of rapid warming or cooling preserved in the layers, scientists gain valuable perspectives on the potential pace and impact of contemporary climate trends. This collaborative approach underlines the importance of integrating empirical evidence with theoretical models to unravel the complexities of Earth's climate history. In this way, the sedimentary archives not only document what has been, but also illuminate pathways forward in our understanding. Beyond their scientific significance, high-resolution sediment records inspire a profound sense of connection to the deep past. Each carefully extracted core represents a tangible link to environments that existed thousands or even millions of years ago, bearing witness to cycles of change that transcend human experience. As we analyze the subtle variations encoded within these layers, we are reminded of the intricate interplay between geological forces and living systems, a dynamic balance that sustains the Earth's habitability. The precision and detail now achievable invite us to reflect on the fragility and resilience embedded within the planet's history, encouraging stewardship grounded in knowledge and respect. This evolving understanding enriches our perspective, fostering a deeper appreciation for the temporal scales and processes that shape life and climate. With these insights in hand, our exploration continues, guided by the ever-unfolding stories preserved in Earth's layers. The layers of Earth's crust are far more than mere geological strata. They are the planet's own archive, chronicling an intricate history of change spanning billions of years. Each sediment layer, volcanic ash deposit, and mineral vein holds clues about ancient environments, shifting continents, and fluctuating climates. Through meticulous study, scientists decode these records to reconstruct past temperatures, atmospheric compositions, and even the rise and fall of ecosystems. This deep time perspective reveals patterns of stability and upheaval, periods of gradual evolution punctuated by sudden transformations that have shaped the conditions necessary for life. Understanding these natural rhythms helps us grasp how Earth's systems respond to various forces, whether internal, like tectonics, or external, like solar radiation. The geological archive thus serves as a vital reference, grounding our knowledge of Earth's dynamic processes within a continuum of time far beyond human lifespan. Among the most compelling stories preserved in Earth's layers are those of ancient climate shifts, recorded in the chemical signatures left behind by long-extinct organisms and trapped gases. Ice cores, marine sediments, and fossilized soils provide a detailed account of glacial cycles, greenhouse gas fluctuations, and ocean circulation changes. These records reveal how climate has oscillated between warm and cold phases, responding to subtle variations in Earth's orbit, volcanic activity, and atmospheric composition. Importantly, they show that life's resilience is often tested by rapid climate transitions that disrupt ecosystems and alter habitats globally. By examining periods such as the Paleocene-Eocene thermal maximum or the last glacial maximum, scientists gain insight into the feedback mechanisms that can amplify or mitigate warming and cooling trends. These ancient lessons inform our understanding of present-day climate dynamics, reminding us that the Earth system is interconnected and sensitive, and that shifts in one component ripple through the entire biosphere. The interplay between geology and climate is further illuminated by the study of Earth's tectonic movements and their influence on atmospheric conditions over millions of years. The drifting of continents has shaped ocean currents and mountain building, which in turn affect weather patterns and carbon cycling. For example, the uplift of vast mountain ranges can draw down atmospheric carbon dioxide through enhanced rock weathering, contributing to global cooling trends. Conversely, volcanic eruptions release greenhouse gases that can trigger warming episodes. This complex feedback loop between the solid Earth and its atmosphere underscores the importance of geological processes in regulating climate stability. By understanding these interactions preserved in rock formations and sedimentary layers, we gain a more comprehensive picture of Earth's long-term habitability. Such knowledge is invaluable as we face anthropogenic influences altering the planet's systems at unprecedented rates. Beyond the scientific revelations, Earth's layered history offers a profound reminder of our place within a vast temporal framework. It invites us to contemplate a resilience of life through epochs of transformation and the delicate thresholds that sustain planetary balance. Recognizing that the environmental conditions we depend upon are the result of intricate and often slow-moving geological and climatic processes encourages humility and responsibility. As human activity accelerates changes in atmospheric composition and land use, the lessons embedded in Earth's layers serve as both caution and guide. They teach us that while the planet has endured immense shifts, the stability we rely on is neither guaranteed nor permanent. This awareness fosters a deeper commitment to stewardship, one informed by the wisdom of Earth's deep past and the imperative to safeguard its future. As we continue to unravel the narratives contained within Earth's layers, we are equipped with a clearer understanding of how past geological and climatic events have shaped the world we inhabit today. This knowledge is not static, but a foundation from which to anticipate and respond to ongoing environmental changes. The records preserved in rock and ice remind us that Earth's systems are interconnected, and that shifts in climate or geology can have profound and far-reaching effects. By integrating these insights into our approach to environmental challenges, we can better navigate the complexities of our changing planet, embracing strategies that honor the lessons of the deep past. With this understanding guiding us, our journey proceeds toward exploring how these ancient stories influence our collective efforts to foster a sustainable and resilient future. Beneath our feet, the Earth holds an ancient archive, a vast chronicle etched into layers of rock, sediment, and ice. Each stratum is a page in a story that spans billions of years, revealing epochs of volcanic fury, oceanic rise and fall, and the slow dance of continents drifting across the globe. These geological layers not only record the physical transformations of our planet, but also preserve the subtle clues of shifting climates, times when the Earth warmed and cooled, when glaciers advanced and retreated, and when ecosystems blossomed or vanished. This silent narrative, written in stone, invites us to pause and listen, to appreciate the deep time that surpasses human history, and to marvel at the processes that have sculpted the world we now call home. The climate history embedded within these layers serves as a vital key to understanding the planet's complex systems. Through the study of ice cores, fossilized pollen, and mineral deposits, scientists decode patterns of atmospheric composition and temperature fluctuations across millennia. These records reveal not only the natural rhythms of Earth's climate, but also the extraordinary resilience and adaptability of life. They remind us that change is a constant, yet the scale and speed of recent shifts present unprecedented challenges. By reflecting on these ancient signals, we gain perspective on our own place within Earth's vast timeline and the delicate balance that sustains life. The story told by Earth's layers is thus not only a tale of the past, but a guidepost for the future. As we contemplate the story written in stone, we come to recognize that the ground beneath us is more than mere soil and rock. It is a living record of Earth's ongoing evolution. Each fossil embedded in sediment, each band of mineral-rich rock, and each trapped bubble in ancient ice captures moments of transformation and survival. These geological and climatic archives encourage a humility born of time, reminding us that our current epoch is but one chapter in a vast and intricate saga. The lessons preserved here inspire a deep reverence for our planet and a commitment to steward its future with care and wisdom. In appreciating the interconnectedness of Earth's systems, we are called to act thoughtfully, honoring the profound legacy beneath our feet. Ultimately, the story written in stone is an invitation to wonder, a call to witness the grandeur of Earth's history woven subtly into the layers that surround us. It is a testament to the power of natural forces that shape not only landscapes, but the very conditions for life itself. As we stand on this foundation, enriched by the knowledge of what has come before, we are reminded of the enduring beauty and mystery of our planet. This awareness fosters a sense of awe and responsibility, encouraging us to cherish and protect the delicate balance that sustains all living things. The Earth's layers are a silent, steadfast teacher, whispering the tale of time, resilience, and the profound interconnection of all life.